This is the lecture for section 7.2, Basic Properties of Groups. We're going to start by introducing a simplified notation for the group operation. While we use the star notation or the asterisk to denote the operation in a group in the definition, in practice we usually just use AB next to each other instead of A star B to denote the product of two elements A and B in a group. Now in the case that the group operation is addition of some kind, we use the plus symbol, so we would write that as A plus B. We now want to show that the identity element in a group is unique, as well as inverse elements. This is theorem 7.5, and the first part tells us that G has a unique identity element. The second part has two cancellation laws. The first, for all A, B, C, and G, if AB equals AC, then B is equal to C, so we can cancel A on the left. And the second says for all A, B, C, and G, if BA equals CA, then B is equal to C, so we can cancel A on the right. And the third part of the theorem tells us that each element of G has a unique inverse. That is, for each A and G, there exists a unique element D in G such that AD is E and DA is equal to E. So we'll start the proof by looking at part 1. So we want to show that G has a unique identity element. And by axiom G3, we know that G has an identity element E, and we'll suppose E prime in G is also an identity element. So this is our standard uniqueness proof where we suppose we have two of an item, and then we want to show that they're equal to one another. So we need to show that E is equal to E prime. Now since E is an identity element, then it satisfies the properties of an identity element, namely for all A and G, A times E is equal to A, and E times A is equal to A. Now these two equalities must hold for all elements A and G, so in particular they must hold for A equal E prime, our second identity element. So if I let A equal E prime in the first equality, we see that E prime times E is equal to E prime. Now since E prime is an identity element, then it must also satisfy these conditions. That is, for all A and G, A E prime is A, and E prime A is A. And these equalities must hold for all A and G, so in particular must hold for A equal to E. And letting A equal to E in the second equality, we see that E prime E is equal to E. So we now have two equations, E prime E is equal to E prime, and E prime E is equal to E. So combining these equalities, we obtain E prime is equal to E. And that's what we needed to show, and thus G has a unique identity element. Now to prove 2, we have our two cancellation laws. So we'll start by supposing A, B, C, and G are arbitrary elements. And to prove the first statement, we'll suppose the hypothesis AB is equal to AC, and we need to show the conclusion B is equal to C. Now by G4, there exists an inverse element D in G for which AD is equal to the identity E, which is equal to DA. So since AB is equal to AC, then multiplying D on the left on both sides of this equality, we obtain D times the quantity AB is equal to D times the quantity AC. And by the associative law G2, this is the quantity dA times B is equal to the quantity dA times C. And dA, by our assumption, is equal to E. So this is EB is equal to EC. That's using our axiom G4. And then EB is equal to B and EC is equal to C. That's by axiom G3. And therefore B is equal to C, and that proves the first cancellation law. And the proof of the second statement will be similar. So we essentially use all four of the axioms to prove the cancellation laws. Next we have part 3 of the theorem. Each element of G has a unique inverse. So for each A and G, there exists a unique element D in G such that AD is equal to E and dA is equal to E. So we'll suppose that A and G is arbitrary, And by axiom G4, we know that A has an inverse D in G, for which AD is equal to E and DA is equal to E. And so, as usual, when we're doing uniqueness, we'll suppose that D prime in G is also an inverse for A, satisfying the same two conditions. So A D prime is E, and D prime A is E. And we need to show that D is equal to D prime. Now, since AD is equal to E and AD prime is equal to E, then we know that AD is equal to AD prime. The cancellation law in 2 then implies that we can cancel A on the left and we'll obtain D is equal to D prime as required. And so therefore the inverse of A is unique. Now that we've shown that the inverse of an element in a group is unique, we can refer to the inverse of an element as opposed to an inverse of an element. And we can use the standard notation A with a -1 superscript for the inverse of an element A in a group. Therefore, whenever an element D satisfies both AD is equal to E and DA is equal to E, we know by the uniqueness that D must be the inverse of A. And we can use the uniqueness of the inverse to prove some properties of it. So this is corollary 7.6. Let G be a group for all A, B, and G. First, we have the inverse of AB, or AB inverse, is B inverse times A inverse. And second, we have the inverse of A inverse is equal to A. So let's look at the proof. So for 1, we'll suppose that A and B and G are arbitrary. And we want to show that AB inverse is equal to B inverse A inverse. Now, AB inverse is by definition the inverse element for AB. So to prove this equality, we want to show that B inverse times A inverse is the inverse element for AB. And since the inverse is unique, if we can show that B inverse A inverse has the property of the inverse element for AB, then it will follow that it is the inverse element. So if we show that it behaves like the inverse element, the uniqueness tells us that it must be the inverse element. So we need to show AB quantity times B inverse A inverse quantity is equal to E, and B inverse A inverse quantity times AB quantity is equal to E. To prove the first equality, let's start with the left side. AB quantity times B inverse A inverse quantity. And this is going to be A times the quantity B, B inverse, times A inverse. That's by G2, the associative law. And the B, B inverse is just the identity. That's by G4, basically the definition of the inverse element to A. And A times E is just going to be A. That's our axiom G3. And AA inverse will be the identity element E. That's again by G4. So that proves the first equality, and a similar proof shows the second equality, and therefore B inverse A inverse has the property of the inverse element for AB, and so by the uniqueness of the inverse element, it must be the inverse element of AB. Thus, AB inverse is B inverse A inverse. And for the second part of the theorem, or the corollary, we need to show that A inverse inverse is equal to A. And A inverse inverse is by definition the inverse element of A inverse. And to prove the equality, we want to show that A has the property of the inverse element of A inverse. Since A inverse is the inverse element for A, then AA inverse is equal to the identity, and A inverse A is equal to the identity. Now, looking at these equations, you can see that they also show that A has the property of the inverse element of A inverse. And thus, A inverse inverse is equal to A. And this proves 2. Now, for repeated multiplication, we're going to introduce exponent notation. So suppose G is a group and A is an element of G. For any positive integer n, we denote A to the n to be just A multiplied times itself n times. We also define A to the 0 to be the identity element. So this doesn't follow from the previous definition. This is a new definition for A to the 0 power. And for any positive integer n, A to the minus n, so since n is positive, minus n will be negative, And this is, by definition, a to the minus 1, or A inverse, multiplied times itself n times. Now the next theorem tells us that the usual exponent rules apply in groups. So this is theorem 7.7. Let G be a group. For all A in G and for all Mn in Z, a to the m, a to the n is just a to the m plus n. So a power times a power results in, to compute a power times a power, we add the powers. And also a to the m raised to the n power will be a to the mn power. So this is a power to a power means that we multiply the powers. Now the proof of this theorem just involves applying the exponent notation in the various cases depending upon whether the integers are positive, negative, or 0. So the proof is not included here. Now while we usually write statements about groups using multiplicative notation, when the group operation is addition of some type, we should write the statements using additive notation. So the following table shows how various expressions translate from multiplicative notation to additive notation. So first off, our operations in multiplicative notation is just AB, and the additive version of that is A plus B. The identity element in multiplicative notation is usually denoted by E, and in additive notation it's usually denoted by 0. The inverse element in multiplicative notation is denoted using a -1 superscript, and in additive notation it's denoted by -a. And our exponents, a to the n is a multiplied times itself n times. In the additive notation, this really translates to n times a, which is a added to itself n times. And so this is a multiple of a. And for negative exponents, we have a to the minus n is a to the minus 1, or a inverse, multiplied times itself n times. And minus n times a will be minus a added to itself n times. And then we can also translate theorem 7.7 to additive notation. So the first part of the theorem says that a to the m times a to the n is a to the m plus n. In the additive notation, this is going to be ma, the multiple of a, plus na is equal to m plus na. And the second part of the theorem is a to the m raised to the n power is a to the mn power. And in additive notation, this translates to n times ma is equal to mn times a. Next, we want to talk about the order of an element. So we'll start with our definition. An element A in a group G is said to have finite order provided that a to the k is equal to the identity e for some positive integer k. In this case, the smallest positive integer n, such that a to the n is equal to the identity, is called the order of A and is denoted by enclosing A in two vertical lines. An element A is said to have infinite order, provided that a to the k is not equal to the identity e for all positive integers k. Now careful, don't confuse the order of an element in a group with the order of the group itself. If you'll recall from the previous section, the order of a group is just the number of elements in the group. And this is very different from the order of an element. As we'll see later, there actually is a connection between the order of an element in a group and the order of the group itself, even though the definitions are independent of one another. For an example, let's find the orders of the following elements in S3. So F is the permutation that maps 1 to 2, 2 to 3, 3 to 1, and G is the permutation that maps 1 to 2, 2 to 1, 3 to 3. To determine the order, we need to find the smallest power of each element that equals the identity. So we'll start with F. F squared is just F composed with itself. And if we compute this composition, so F maps 1 to 2 and then 2 to 3, 2 to 3, 3 to 1, 3 to 1, 1 to 2. So f squared will be the permutation that maps 1 to 3, 2 to 1, and 3 to 2. And this is obviously not the identity, so we'll continue. F cubed is f squared composed with f, and so this will be the permutation we just computed, composed with the original permutation f. And if you compute this out, this turns out to be the identity permutation. So that tells us that 3 is the smallest power of f that equals the identity, and therefore the order of f is equal to 3. And now we can look at g. So g squared will be the permutation composed with itself. And let's see, g maps 1 to 2 and then 2 back to 1. G maps 2 to 1, 1 back to 2. And then g fixes 3, so 3 maps to 3 and again maps to 3. So this will be the identity permutation, and therefore the order of g is 2. 2 is the smallest power of g that equals the identity. For another example, we can find the orders of the elements 3 and 6 in the group Z8, where the operation is addition modulo 8. So we need to find the smallest power of each element that equals the identity. And now since our operation is addition, the identity is 0, and the powers are actually multiples. So the multiples of 3 are 1 times 3 is 3, 2 times 3 is 6, 3 times 3 is 9, which in Z8 is equal to 1, 4 times 3 is 12, which in Z8 is equal to 4. 5 times 3 is 15, which in Z8 is 7. 6 times 3 is 18, which in Z8 is 2. 7 times 3 is 21, which in Z8 is 5. And 8 times 3 is 24, which in Z8 is 0, which is our identity element. So the smallest multiple of 3 that equals the identity element is 8. And so the order of 3 is equal to 8. Now the multiples of 6 are, well, 1 times 6 is 6, 2 times 6 is 12, which is 4 in Z8, 3 times 6 is 18, which is 2, and 4 times 6 is 24, which is 0, our identity element. So the smallest multiple of 6 that equals the identity element is 4, and therefore the order of 6 is equal to 4. For one more example, let's find the order of each of the elements in U9, which contains 1, 2, 4, 5, 7, and 8. If you'll recall from the previous section, U9 is the group of units in Z9 under the operation of multiplication, mod 9. And from a theorem way back in chapter 2, I think, okay, an element is a unit in Z9 if and only if it's relatively prime to 9. So the units in Z9 are 1, 2, 4, 5, 7, and 8. So now the identity in U9 is 1, which just has order 1. The powers of the non-identity elements along with their orders are, so for 2, we have 2 squared is 4, 2 cubed is 8, 2 to the 4th is, well, 2 to the 4th will be 2 times 2 cubed, which is 16, which is 7. 2 to the 5th, that's 2 times 2 to the 4th, which is 14, which in U9 is 5. And 2 to the 6th will be 2 times 2 to the 5th, which will be 2 times 5, which is 10, which is equal to 1 in U9. And so the smallest power of 2 that equals the identity element 1 is 6. So the order of 2 is 6. For 4, we have 4 squared is 7. 4 cubed is 1. So that's the identity element. So the order of 4 is 3. 5 squared is 7. 5 cubed is 8. 5 to the 4th is 4. 5 to the 5th is 2. 5 to the 6th is 1. That's the identity. So the order of 5 is 6. 7 squared is 4, 7 cubed is 1, so the order of 7 is 3. And 8 squared is 1, so the order of 8 is 2. So those are the orders of each of the elements in U9. Next we have theorem 7.8, and this has some properties of the order. So let G be a group, and suppose A is an element of G. Now if A has infinite order, then for all K and Z, the elements A to the K are distinct. And part 2 tells us that if A to the I is equal to A to the J, for some integers I and J, with I not equal to J, then A has finite order. Now, note that the first statement is actually the contrapositive of the second statement. So it suffices to prove just one of the two statements in the theorem. So we'll prove the second statement. So we'll suppose that A to the I is equal to A to the J for some integers I and J with I not equal to J, and we need to show that A has finite order. To show this, we need to show that A raised to the power K is equal to the identity for some positive integer K. That's just the definition of an element having finite order. Now, since I is not equal to J, then one of I or J is greater than the other. So we'll assume that I is greater than J. Multiplying both sides of our hypothesis, A to the I equal A to the J, by A to the negative J, we obtain A to the I, A to the negative J, is equal to A to the J times A to the negative J. And this is A to the I minus J on the left, and A to the 0, which by definition is the identity element E, on the right. And since I is greater than J, then I minus J is greater than 0, so I minus J is a positive integer. So what we now have is we have A raised to a positive integer power is equal to the identity, and so this implies that A has finite order. And this proves the second statement, so proves the theorem. Next, we have theorem 7.9, and this has some additional properties of the order. So let G be a group, and suppose A and G is an element of finite order n. Then first, for all integers k, A to the k is equal to the identity if and only if our order n divides k. Second, for all integers I and j, A to the I is equal to A to the j if and only if A is congruent to j mod n. And third, for all positive integers d and t, if n is equal to t times d, then A raised to the t power has order d. So we've got three statements here. We'll start with 1. So we want to prove for all integers k, A to the k is equal to E if and only if n divides k. So suppose k is an arbitrary integer, and we need to prove that A to the k is equal to E if and only if n divides k. This is a biconditional, so we need to prove our two directions. So we'll start with the forward direction. Suppose A to the k is equal to E, we need to show that n divides k. By the division algorithm, dividing n into k, there exists integers q and r such that k is equal to nq plus r, and 0 is less than or equal to r is less than n. So our divisor is n now, and our remainder r is greater than or equal to 0 and less than n. Now we want to show that the remainder r is equal to 0. This will imply that n divides k. So we'll use a proof by contradiction. Suppose r is not equal to 0, which means that r has to be strictly positive. We then need to derive a contradiction. Now since A has order n, then we know that A to the n is equal to E. Then A to the k, which is A to the nq plus r, which will be A to the nq times A to the r, which is A to the n raised to the q power times A to the r. And this will be E raised to the q power times A to the r, since A to the n is equal to E. and the identity raised to any power will just be the identity, so this will be a to the r. Now by our hypothesis, we're supposing that a to the k is equal to e. So a to the k is equal to a to the r, and a to the k is equal to e, so this implies that a to the r is equal to e. However, r is strictly less than n, and n is the order of a, which means that it's the smallest positive integer power of a that equals the identity. So this is a contradiction. We have a positive integer power of a that equals the identity that is smaller than the smallest positive integer power. And therefore, r must equal 0, which means that k is equal to nq, and therefore n divides k. And this proves the forward direction. For the backward direction, we'll suppose n divides k, and we need to show that a to the k is equal to e. Well, since n divides k, then k is equal to nt for some integer t. Since a has order n, then a to the n is equal to e. Then a to the k is a to the nt, which will be a to the n raised to the t power, and a to the n is equal to e, so this will be e to the t power, which is just e. And this proves the backward direction, and this completes the proof of part 1 of the theorem. We'll move on to part 2 now. So for all integers I and j, a to the I is equal to a to the j, if and only if I is congruent to j mod n. For the proof, suppose I and j are arbitrary integers. We need to prove the biconditional statement a to the I is equal to a to the j, if and only if I is congruent to j mod n. So we have to again prove both directions. So for the forward direction, we'll suppose a to the I is equal to a to the j, and we need to prove I is congruent to j mod n. Now multiplying our hypothesis by a to the negative j, we obtain a to the I times a to the negative j is equal to a to the j times a to the negative j, and this is a to the I minus j equals a to the 0, which is the identity. Now by part 1, since a to the I minus j is equal to the identity, this implies n divides I minus j, which implies that I is congruent to j mod n. And this proves the forward direction. For the backward direction, we'll suppose I is congruent to j mod n. We need to prove a to the I is equal to a to the j. Now since I is congruent to j mod n, then n divides I minus j, and by part 1, this implies a to the I minus j is equal to the identity e, and multiplying both sides of this equation by a to the j, this implies a to the I minus j times a to the j is equal to e times a to the j, and this simplifies to a to the I is equal to a to the j. And this proves the backward direction, and this completes the proof of part 2 of the theorem. And moving on to part 3, for all positive integers d and t, if n is equal to td, then a to the t has order d. So we'll suppose that d and t are arbitrary positive integers. We'll suppose our hypothesis n is equal to td. We need to show that a to the t has order d. To show this, we need to show that a to the t raised to the d power is equal to e, and d is the smallest positive integer power of a to the t that equals the identity. Now since a has order n, and n is equal to td, then a to the t to the d is a to the td, which is equal to a to the n, which is equal to the identity. So this is the first part of what we need to show. To show the second part, that d is the smallest positive integer power of a to the t that equals the identity, let's suppose that k is an arbitrary positive integer such that a to the t to the k power is equal to the identity. So we're trying to show that d is the smallest positive integer power of a to the t that equals the identity, and k is another positive integer power of a to the t that equals the identity. So we want to show that k is greater than or equal to d. So D is smaller than K. Now since A to the T to the K is equal to ATK is equal to the identity, then by part 1 of our theorem, N divides Tk. And this implies that Tk is equal to Rn for some integer r. Now substituting n is equal to Td into this equality, we obtain Tk is equal to Rtd. Since t is positive, then canceling t from both sides, we obtain k is equal to Rd. And this implies d divides k, and since d and k are both positive, this implies d is less than or equal to k, as required, and thus a to the t has order d. And this proves part 3 of the theorem. As an example, if you'll recall from our previous example, the orders of the elements in U9 are as shown, and the element 2 has order 6, which is 2 times 3. So by part 3 of the theorem, 2 squared, which is 4, should have order 3, and we see that it does. And 2 cubed, which is 8, should have order 2, and again we see that it does. Next we have corollary 710, and this tells us let G be an abelian group in which every element has finite order. If C in G is an element of largest order in G, that is, the order of A is less than or equal to the order of C for every element A in G, then the order of every element divides the order of C. To prove this result, we'll need the following result, which appears in a homework exercise. Let G be a group, and let A and B be elements of G with finite orders, order of A and order of B. If A and B commute, that is, AB is equal to BA, and the order of A and order of B are relatively prime, then the AB, the element AB, has order of A times the order of B. So the order of the product AB is the product of the orders of A and B. So let's start the proof of the corollary. So we'll use a proof by contradiction. So we'll suppose the corollary is false. So we're going to suppose that C in G is an element of largest order in G, but there exists an element A in G whose order does not divide the order of C. So our hypothesis holds, but our conclusion does not. We then need to derive a contradiction. Now, since the order of A does not divide the order of C, then there must be a prime P that appears to a higher power in the order of A than it does in the order of C. So let's suppose that P appears to the power R in the order of A and to the power S in the order of C, where R is strictly greater than S. Then the order of A will be P to the R times M, and the order of C will be P to the S times N for some integers M and N, for which P and M are relatively prime and P and N are relatively prime. So if we basically assume that R is the power of P that appears in the order of A, and S is the power of P that appears in the order of C, then we obtain the order of A is P to the R times M, and the order of C is P to the S times N. And there's no other factors of P in M and N. Now by part 3 of theorem 7.9, the order of A to the M will be P to the R. Okay, so since the order of A is the product P to the R times M, then the order of A to the M will be the remaining factor in the product, so P to the R. And the order of C to the P to the S will be N. Now since G is abelian, A to the M and C to the P to the S commute. And since the order of A to the M, which is P to the R, and the order of c to the p to the s, which is n, are relatively prime, then the homework exercise implies that the order of a to the m times c to the p to the s will be the product of the two orders, which is equal to p to the r times n. Now, since r is greater than s, this order, p to the r times n, is greater than the order of c, which is p to the s times n, which we suppose was the largest order in G. And so this is a contradiction. We obtained an element in G which has a larger order than the element with largest order. And thus the corollary holds. For an example of how we can apply the corollary, the order, if we look at the orders of the elements in U9 again, there is shown. And the largest order of an element in U9 is the order of 2 or the order of 5. They're both equal to 6. And we see that all the other orders in the group divide 6. So the other orders are 1, 2, and 3, each of which divides 6. Okay, so this finishes up section 7.2.